Gracias. Como dicen, yo soy de UT Arlington, soy profesor de física allá. Soy puertorriqueño y nací en los Estados Unidos y por eso toda mi educación es en inglés y por eso voy a dar la charla en inglés. Antes de empezar la charla científica, quiero decir algo de UT Arlington, que estamos buscando estudiantes para programa graduado. Tenemos montones de área de research, tenemos dinero, becas, toda esa cosa, y nadie tiene información de lo que tenemos allá. Pero tenemos high energy physics, condensed matter theory and experiment, nanobiomaterials, astrophysics y también space physics, en que yo trabajo. And it's very important to study physics. And before I talk about space physics, I want to talk about what happens when you don't study physics. Aquí tenemos un ejemplo de la consecuencia de no estudiar física. Por eso es muy importante estudiar física. Okay, so to talk about space weather and storms from the sun. The sun is always changing, and here we see a composite movie from SOHO and TRACE, two satellites. ¿Puede bajar la luz un poquito? We see a composite image of SOHO, TRACE, various instruments on SOHO that are looking at the outer corona, the inner corona. The green is X-ray on the surface of the sun, and you see all kinds of activity. I'll play it over again. You see these large puffs of material, ionized material, plasma with embedded magnetic field coming off the surface of the sun, often coming from active regions that might develop into solar flares or coronal mass ejections, and these are associated with sunspots. And we live with a variable star. We live with a variable star, and those variations cause changes in our environment. And that is really what space weather is about, understanding those changes and how they affect us here on Earth and our technology. And a fundamental fact about the sun, in fact, of all stars, is that they're magnetized bodies. Dynamo processes in the sun convert convective motion and rotational motion into magnetic field through magnetohydrodynamic interactions in the exterior convection zone of the sun. And we can see the effect of that by looking at pictures like this that are ultraviolet pictures. Here you see this material lifted off from the surface of the sun. This is called a prominence. And this is billions of tons of material being held up against solar gravity by magnetic field. Those magnetic forces can be very strong, and they dominate the outer atmosphere of the sun. All of that churning, boiling motion in the outer photosphere twists up the magnetic field, converting mechanical energy into magnetic energy. And sometimes that is released in very spectacular ways, as we see here in this solar flare. You see this eruption. The bright light, this is all X-rays, by the way, so that's 2 million degrees Kelvin, the bright regions there. And you see that arcade loop forming. You see the outline of these loops of magnetic field. This activity is always going on in the sun, both on the large scale producing these large eruptions, the solar flares, and also on the small scale, continuing small micro flares which heat the upper atmosphere of the sun. Here we see an image in X-ray from the Yoko satellite imager of several years ago. And X-rays are produced by very hot material. So the dark regions are cool. They're only 500,000 degrees. And the bright regions are hot. They're up to 2 million degrees. When the first spectroscopic observations were made in the 40s of the solar atmosphere, and it was discovered that there were things like oxygen 7+, so oxygen ionized, so 7 electrons are taken away, leaving only 1, very high charge state. Those observations at first were not believed. In fact, at first people thought that there were new elements being discovered because there was strange spectroscopic signatures. And remember that we discovered helium on the sun before we discovered it on Earth, by seeing the spectrum of helium and realizing that it was different from every other atom. So that was the first thought. Maybe they're new elements. Well, no, they're not new elements. It's just a very, very hot atmosphere. And it was difficult to understand how that could happen. The photosphere is 6,000 degrees. How can you have a surface of a star be 6,000 degrees and the atmosphere be 1 million degrees? And the answer is the solar magnetic field. It's converting mechanical energy into magnetic energy, and then that magnetic energy is dissipated in heat through processes, including something called magnetic reconnection, in which magnetic energy is destroyed and converted into plasma, thermal and kinetic energy. In fact, the atmosphere of the sun is so hot that gravity can't hold it down. So gravity's pulling down on the solar atmosphere, and the pressure is pushing out. And if the pressure pushing out is great enough, then it just keeps on pushing, and the atmosphere accelerates. If you take a hose with water flowing through it, and you put your thumb over the end, and you start to close it off, what happens? The water coming out speeds up. And that's the same thing that happens in the solar atmosphere. Now gravity is the nozzle. And eventually, the solar atmosphere becomes supersonic and flows out to fill all of the space between the planets throughout the whole solar system. And we call that the solar wind. Now, when the solar wind encounters a magnetized body, or even unmagnetized bodies like comets, but let's limit ourselves to objects with magnetic fields. The magnetic field exerts a force on the solar wind. And the solar wind exerts a force back on the magnetic field. These are basic principles that you should be learning in your first 2 years of physics. Forces are always interactions between two objects. Object A exerts a force on B, B exerts the force back on A. Equal and opposite. In electricity and magnetism, you learn about the Lorentz force, QV cross B. These are the basic principles that allow us to understand what happens in space. So the solar wind flows, hits the magnetic field of the Earth, and compresses it on the day side and stretches it out on the night side, making a cavity in the solar wind called a magnetosphere. And a magnetosphere looks like a comet, for the same reason that a comet looks like a comet. And we can see how this happens with this simulation. Here's the magnetosphere. That black circle is not the Earth. It's 3.5 times the size of the Earth. And this is an animation which is not just a cartoon. It's an initialization run from one of our simulations. Fully three-dimensional magnetohydrodynamic simulation of the solar wind magnetosphere interaction. I'll play this over again. So you see the solar wind blow in and distort the original dipole field into this comet-shaped magnetosphere. Now we use the language of forces, pushing on magnetic field and magnetic field pushing back. But really what happens is that there are shears in the magnetic field. There's a curl of the magnetic field, which means that there's a current there from Ampere's law. And what's happening is that large current systems are being generated, which distort the Earth's magnetic field into the shape of the magnetosphere. And these currents flow through space, and they're large. Anywhere on a quiet day, it's 1 million amps. On a storm day, it's 10 million amperes of current integrated that's flowing through space around Earth. And some of this current flows along Earth's magnetic field into and out of the polar regions. And here we have an artist's diagram of that. You see these sheets of electric current flowing in and out of the polar region, and the artist has drawn some light coming from there because these currents that flow along the field line light up the sky, and that's what we call the aurora. Has anyone here ever seen aurora? Raise your hand if you have. So a few people. It's pretty remarkable. This is the Geophysical Institute at the University of Alaska in Fairbanks, and this is outside of Fairbanks, Alaska. This is what it looks like when you're at 300 kilometers in altitude, space shuttle altitudes. The bottom of the emission region is about 110 kilometers, and it goes up to about 200 kilometers. And that's just the place where the light is coming from. There's electric current in a sheet going all the way up, out into distant space, connecting to this flow of the solar wind past the Earth's magnetosphere. And it's that flow, kinetic energy extracted from that flow, that powers this system. Only a very small amount of the energy coming past the Earth is actually captured. It's about 1%. But that 1% is enough to power all of the activity that we see. And if you go to higher altitudes, now at about 3 Earth radii looking down in ultraviolet, we see that the aurora forms a ring centered on the geomagnetic North Pole, not the geographic North Pole, which is here. And this is the day side of the Earth that's lit up by the sun. And the aurora is in both hemispheres. Here you see a movie. You see it brightening in both. The green is real data. This is from a spacecraft called Image. Superposed on that is the map of the continents so that you can have a sense of scale and time. And I'll play this over again. But you can think of the aurora as 2 rings, and they're connected by the magnetic field, and that energy is being dumped into the ionosphere. What we see at Earth, we see at other places as well. Here are some pictures from the Hubble Space Telescope of Saturn and Jupiter, and you can see rings around the poles of Saturn and also around Jupiter. Now in Jupiter, there's this curious feature right there, and then you see the mirror image of it up here in the northern hemisphere, that line which is equatorward, detached from the rest of the aurora. That is the magnetic footprint of the Galilean satellite Io. It's the orange one, the one with all the volcanoes. Io is always dumping material into Jupiter's magnetic field. That material becomes ionized through various processes and fills a tube of magnetic field centered on the moon Io. That tube of magnetic field filled with material acts as a generator, creating an electrical circuit that is powered with about 20 million amps of current that goes down into the ionosphere of Jupiter, lighting it up and leaving a footprint of the moon that can be seen from Earth. Now, all of this research into magnetospheres, magnetic fields, actually has a very, very long history. And the story really begins with De Magnete, which was a book written in 1600 by William Gilbert. And it's considered to be the first book of the scientific era. And this is well before Newton's Principia, because this book was the first one to systematically examine phenomenon. And Gilbert himself, he was a physician. He was the chief physician to Queen Elizabeth I. And in his spare time, he studied magnetism, and he wrote it all down. He did experiments to show that magnetism was not related to garlic, because back then people thought that you could take a piece of metal and rub it with garlic and make it into a magnet. Well, he tried it, and it didn't work. But he did all kinds of experiments with magnetism, and in fact, he determined that the Earth is a great magnet. And that's why a compass needle points north. And in fact, in the title, it says, on the study on magnetic fields, on the body of magnetism, and the Earth itself is a great magnet. That's the Latin in the title of the book. Once people understood that the Earth was a magnet, now they knew how a compass worked, and compasses were very important for navigation. The problem was that true north and magnetic north are not in the same place. And people knew this already by the time of Columbus. When Columbus sailed across the Atlantic, he started noticing that the position of the compass needle relative to the North Star started changing. And he kept one log with that information, and he didn't tell his crew, because they would have killed him and mutinied and gone back to Spain. Because for them, the compass was magic. And he told the crew that the compass was pointing in the right direction. But he recorded in his secret log that it wasn't. And he didn't know what it meant. But if you go far enough away from that prime meridian, then you start to see these differences, and people needed to know what they were and have a map so they could convert a compass reading into a real direction. And it was very precise measurements of the position of compass needles that led to the discovery of what we now call magnetic storms. In 1724, this paper was published. Actually, this is the cover from the Philosophical Transactions of the Royal Society, and the last one here is the paper by George Graham, who was a watchmaker. Now, to make watches, you had to make very precise instruments, and so he was very well suited to being an experimental physicist, although he was a watchmaker. But he was a fellow of the Royal Society and did many investigations and published his results. And in 1724, he wrote a paper saying, well, I was trying to make very careful observations near London, and the needle started wiggling. And he closed it up in a glass case, and he made measurements in the daytime, at night, when it was cold, when it was hot, when it was raining, when it was not. Sometimes the wiggles were there, sometimes they weren't. And he had no explanation what these wiggles were. But he reported them, irregular variations of the compass needle. Not long after that, scientists in Sweden discovered that when the needle started to shake, there was aurora overhead. So they made a connection that maybe these two things are related. And then Gauss, those of you who are in your third year probably have had your fill of Gauss and the divergence theorem and Gauss's law and all of that. He developed that mathematics to deal with the problem of magnetism. That's what he was really interested in, was magnetism. And he recruited his friend, Alexander von Humboldt, the explorer, to set up observatories all over the world, while Gauss set up observatories in Europe in what he called the magnetic campaign, to understand Earth's magnetism. And like I said, a lot of the math that we study in mathematical methods of physics, he developed to deal with magnetism. But these observations across the world showed that these irregular variations, these magnetic storms, were global. What could produce a change in the magnetic field across the whole Earth at the same time? Very mysterious. Also mysterious was the aurora. Scientists have been interested in the aurora for centuries. They wanted to know what it was, and there were lots of ideas like light reflecting off of ice crystals, things like that. But the first electrical theory of the aurora was produced by Benjamin Franklin. Now, in the United States, we consider Benjamin Franklin one of our founding fathers and politician and all of that. But in his time, he was famous because he was a scientist. He was the first person in the Americas to be elected both to the Royal Society of London and to its equivalent society in France. And that did not happen again for another 150 years. Historians of science talk about Benjamin Franklin and the period where he came up with the ideas of electricity as the age of Franklin, in between Newton and Maxwell. He was that important. Positive and negative in electricity, that came from Franklin. Franklin gave us the first scientific theory of electricity. And he also gave us the first theory of the aurora. And he thought it came from thunderstorms, a reasonable thing for him to think about. So he said, this is a figure from his paper. He said, there's hot air in the tropics, and the hot air rises and goes to the polar region where it condenses and creates thunderstorms, and then it circulates back down. Now, 50 years later, an English scientist by the name of Hadley also thought of this idea, but talked about it in terms of weather, and we now call these Hadley cells. But Franklin did it first. So the modern study of the aurora and of the space environment began around 1900. And it was pioneered by Christian Birkeland, a Norwegian who was a very brilliant scientist and did pioneering work in electromagnetism. In fact, he wrote a paper on the uniqueness of the Poynting vector in 1898 that was cited nearly 100 years later in the American Journal of Physics as still being relevant to the question of fundamental electromagnetism and the uniqueness of the Poynting vector. Very surprising that anybody could write a paper that would still be read and that you could get information from nearly 100 years from then. And in addition to being a brilliant theorist, he was a good experimentalist. And here we see him in his laboratory. This is a picture from his book, published in 1913, where he put together all the information of the aurora. He made vacuum chambers in which he put a magnetized sphere that he called a terrella. And then he injected what he called cathode rays, electrons. Remember, he didn't know about protons. He only knew about electrons. And sometimes he would get rings of light around the polar regions. That, combined with observations of the magnetic field, some of which he carried out himself, going up into the mountains of Finland in the wintertime to set up observatories. He almost died in one of those expeditions. His stories about that are quite interesting reading. I like physics, but I'm not going to die for it. So he came up with ideas, including the notion that electric current was coming from space directly into Earth's atmosphere and making it light up. His ideas had some problems, though, because he talked about beams of electrons from the sun. Well, those will disperse because of the repulsion. He didn't know about protons. And then somebody said, well, if that's happening, then the sun will charge up positive. And he said, well, maybe we need to add a term to Maxwell's equations, which was wrong, because he was working with incomplete information. And this is something you have to realize, is that scientists always work with incomplete information. We do the best that we can at the time, but usually we argue about it. And that's the most fun, is the argument. And in fact, scientists argued about Birkeland's ideas for a long time. These two pictures make it look like these guys are the same age, but they were separated by 30 years. Sidney Chapman, who provided the first scientific theory of the ionosphere, and many, many other things. And Hannes Alfvén, who was 30 years younger, a Swede who pushed Birkeland's ideas. Chapman didn't agree with a lot of what Birkeland said, and Alfvén and Chapman fought all the time. Chapman being the senior scientist in the field, and Alfvén being the young guy fighting. And Alfvén would always say, when we fly satellites, we'll see who's really right. And in fact, with the space age, we could go and see for ourselves. And he was right about many of these things. So he won the Nobel Prize, and he didn't. So when we finally flew into the space environment, we discovered all kinds of things. We found things that we didn't expect, like the Van Allen radiation belts. Here is a two-scale drawing of the Van Allen radiation belts with part of it cut out so you can see. There's an inner region and then an outer region, and this is regions of trapped high-energy particles, trapped in Earth's magnetic field. That was the first major discovery of the space age. But we discovered other things like the whole structure of Earth's magnetosphere and all of the complicated current systems. Some of them I've already talked about, currents that flow along the magnetic field in and out into the polar regions, but there are currents that flow across the night side, currents that flow around the Earth. This current, ring current, that flows around the Earth like that in the equator is what was causing the magnetic storms. We discovered all of those things over the years. We flew into the solar wind. We've flown to the other planets and discovered the magnetospheres of other planets, of Jupiter, of Saturn, Mercury. And we discovered these coronal mass ejections. We finally figured out what was making big disturbances in the Earth's magnetic field. These large blasts of material coming off from the sun. The sun is the white circle. And then this is a metal disk in the telescope, which allows us to get an artificial eclipse. That's the UFO. No, that's a planet. But you'll find stories on the internet where people will say, I've made a discovery. NASA's been hiding UFOs in their images. But don't believe everything you read on the internet. I'm going to play this over again. When these large clouds blast out through the solar wind, they pile up the material in front of them into a shock wave. And there's a jump in the magnetic field across the shock wave, which means there has to be an electric current there. And if there's a current, there's an electric field, which is pushing that current. So there's an electric field along the face of the shock. And if a particle gets trapped in the shock face and drifts along that electric field, it will gain energy. And so you see these streaks of white light in the image, like, let me play it again. There's one bit in particular that's very strong. And what you're seeing are actually energetic protons that have been energized in interplanetary space and are hitting the camera, hitting the detector, causing those bits of white light, like right there, all of that streaking there. So that's a blast of energetic protons, which can be pretty intense for a spacecraft. Now, all of this is very interesting, but why should we care about it? Well, our technology is based on electromagnetism. Look around this room. What if we had no electromagnetism as part of our technology? First thing, I wouldn't be able to give this talk. Second thing, we'd all be sitting in the dark. Nobody would have their cell phone or computers or watches. Nobody carries around a wind-up watch anymore. It's all based on electricity and magnetism. Our entire civilization is based on electricity and magnetism. It is as basic to us as fire. And if ever humans were to have such a catastrophe as to lose the knowledge of electricity and magnetism, I would say that catastrophe would probably be big enough to just completely wipe us out as a species. Now, we don't know who discovered fire. We don't even know if they had names as we would recognize them. How far back in our history, did Homo erectus have language the way that we have? They certainly had fire. But we do know the names of the people who discovered electromagnetism. We do know the names of Franklin and Ampere and Maxwell and Faraday and the others. Coulomb, all the names that you learn, all the laws, if you will, that you learn in electricity and magnetism. These are the people who discovered fire for us. And everything we do is based on electromagnetism. And all of these effects are electromagnetic that we see with space weather. And so they can affect what we do in pretty profound ways. And in so many different ways that collectively we need to understand it to protect our societies. Certainly these high energy protons, solar flare protons, can damage spacecraft, but they can also harm astronauts. When those electric currents flow through the atmosphere heats up. Just like when you put a current through a wire, there's Joule heating, I squared R. So the atmosphere heats up. When it heats up, it puffs out. And when it puffs out, there's increased drag for low altitude spacecraft, and so you can have problems with satellites. When those currents are flowing through the ionosphere, they're not steady currents, they're highly irregular. They can cause little bubbles of plasma, and that will cause scintillation of radio signals. So if you're trying to communicate with GPS, the signal is going to be bent slightly because there's a change in the index of refraction. And if you're trying to communicate with high-frequency radio, you may lose connection completely, which causes a real problem for, say, airline flights. If you fly from North America to China, you go over the North Pole. So you go through a region where, first of all, you can receive a dose of solar flare protons because that magnetic field is open to the solar wind, but also the communication to the aircraft can be cut off. So when these storms happen, they divert the polar flights, and instead of going to Beijing, you end up in Tokyo, and you're going to spend about another 10 hours in Tokyo until they can get you to Beijing. So there's all kinds of things, and even here on the Earth, there are effects of these ionospheric currents that can cause disruptions to our power grids, as I'll point out in a moment. This business of changing stuff in orbits in space is actually very important. You might have heard recently about a collision of two satellites that created a lot of junk in space. Well, we track all of that so that nothing else runs into the junk. This blue line is a measure of magnetic storminess, something called AP, the planetary index. So when it's big, the magnetic field is disturbed. That means that there's these electric currents flowing through the atmosphere. And these orange bars are the satellites or objects that are being tracked that are not where they're supposed to be. And then it takes a couple of orbits to reacquire the orbital characteristics. And once you know those orbital characteristics and can figure out what the drag is, then you can predict the position of these things fairly accurately. But look what happens. When we get a big storm, all of a sudden there's a bunch of stuff that's not where it's supposed to be. That's because the atmosphere has expanded and produced drag on those objects. All of this activity in the magnetosphere actually can cause the energization of particles inside the magnetosphere. The magnetosphere turns out to be an efficient accelerator. And this is an image from a NASA spacecraft called SAMPEX. These are electrons greater than 3 million electron volts. This is distance from the Earth in this direction. This is day of year in this direction. And then the color tells you how much electrons there are. And red means a lot, and blue means not too many. So here is the normal radiation belt that I showed you that drawing before. That, you see, it's trapped between those two, between 4 and 5, roughly. That's the radiation belt. Not a lot here, not a lot here. And we come along, and here's a big magnetic storm, and look what happens. All of this gets filled in. Here, here, and here were satellite failures. And these are the ones that are public. There were a lot that were not public. Like Motorola lost some of the Iridium spacecraft, but they weren't allowed to talk about it because that was a private thing. We know that they lost them because they built more and sent more up. And people said, well, why are you building more? We're not telling anybody why we're building more. So, but people figured it out. If they're building more and launching more, it's because they lost some of the ones they had. And that one right there, that failure was Galaxy 4, which was carrying 90% of the pager traffic in the United States. It was also carrying feed for NPR and PBS. So that day, all of a sudden, the pagers didn't work in the United States. So, doctors didn't get their calls, drug dealers didn't make their deals, So it can have real effects. All of these changes in the ionosphere, here again is another way of visualizing the changing magnetic field. When this gets negative, this white line, that means that there's a lot of magnetic disturbance. This is called the storm time disturbance, DST. When there's a big changing magnetic field, changing magnetic fields induce electric currents in nearby conductors. And what do humans like to do? We like to build big conductors. We call them power transmission grids. We call them pipelines, communications cables. But we build big, long conductors, which are big antennas for space weather, collecting this power and putting it into our power grid. And that can have some pretty severe effects. For example, transformers convert high voltage, low current to low voltage, high current, so that we can send the high voltage, low current and minimize power dissipation for long distance transmission. But they're working with AC. And they don't like DC current because that can really mess up a transformer. And that's what can happen on the inside of a transformer when you put DC current from a magnetic storm into a transformer. That's the inside of one of those, a big transformer at a typical substation. That's about a $10 million transformer. And in 1989, there was a magnetic storm that blacked out all of Quebec. And it almost got into New York, which would have been much more expensive if they hadn't stopped the cascade failure there. Texas is isolated. We have our own power grid. We're our own country. And the sun can generate activity at almost any time. In October of 2003, we saw this in Halloween. We call them the Halloween storms. So here's a white light image of the sun. And here we are in early October. There was nothing going on. And all of a sudden, one huge sunspot, and then another huge sunspot, and then a third huge sunspot came up out of the surface of the sun. And these bundles of magnetic energy released a lot of activity. And here we see, again, a composite image from the various SOHO imagers, all the stuff that was going on. There were just a series of coronal mass ejections that blasted out through space, especially big ones like that were coming right at us. And there were effects. First of all, this was a solar system storm. These clouds blasted out through the inner solar system past Earth, but we had satellites at Jupiter and at Saturn, Ulysses and Cassini. They saw these things. The clouds went out to the edge of the solar system, and the Voyager spacecraft at the very edge of the solar system saw these clouds come by. These were solar system storms. They had effects on Earth. There were 2 damaged Japanese communication satellites. One was permanently lost. Lots of other spacecraft had problems and had to be shut down. There was a blackout in Sweden. Mars Odyssey was on the way to Mars at the time, and it has an instrument called MARIE to measure the radiation environment to try to determine what astronauts will face on the way to Mars. MARIE was knocked out. When they managed to recover the data 2 weeks later, it was discovered that the radiation was so intense that if somebody had been standing on the surface of Mars in 2 hours, they would have been dead. When you're standing on Mars, you have almost no atmosphere and almost no magnetic field. Now, there's a planet, okay, that blocks half. But you have 2 pi steradian open to space. And all of that is going to come down. And if you're outside of the protection of Earth's magnetic field and Earth's atmosphere during one of these events, you will receive a lethal dose of radiation. So going to Mars is a difficult thing, but it's even more difficult to keep them alive. And I'm sure that they're very interested in doing that. There was also Aurora in Florida, Georgia, Texas. That's Florida. That's northern Florida. And there's Texas and Indiana. It was a big storm. So we want to be able to predict these things. And we're at the point where physics-based simulation models can actually reproduce real events. And what we're trying to do is to build space weather models that go all the way from the surface of the sun to the upper atmosphere of the Earth. And that's the goal of a center called the Center for Integrated Space Weather Modeling, which is funded by the National Science Foundation in the United States, which is like your CONOCYT here in Mexico. And the Center for Space Weather Modeling is all over the country. We have institutions from Boston to Berkeley. It's headquartered at Boston University, but there's Boston, Dartmouth College, University of Maryland, Alabama A&M University, Rice University, my group at UT Arlington, University of Colorado Boulder, and the National Center for Atmospheric Research in Boulder, University of California, Berkeley, Stanford, and then SAIC in San Diego. So we've got groups at all of these places working together to put together a whole story with 4 basic models. One model for the solar corona, one model for the solar wind, another model for Earth's magnetosphere, and then a model for the ionosphere. And there's lots of other pieces of physics that we have to build in. Like, we don't really understand why a solar flare happens. Nobody does. We're trying to figure that out. Why do active regions form on the sun? And can we predict when they're going to erupt? Once they do erupt, can we predict if there's going to be a big blast of solar energetic particles, and where are those particles going? In the Earth's magnetosphere, we still don't understand how all the pieces fit together, how the radiation belts and the ring current are formed, how the magnetosphere and ionosphere couples together. There's a lot of basic physics. But the kind of physics that we deal with is not quantum mechanics. It's electricity and magnetism. It's the kind of thing that many of you are studying right now in your courses. And that, as I say, it's very basic physics, but in real life, complicated situations. And the simulation that I work with is the magnetosphere simulation, the Lyon-Fetter-Mowbray code. It's a fully 3-dimensional magnetohydrodynamic simulation of the solar-wind interaction with the magnetosphere. And this is the only math that I'll show. But this is MHD. This first equation is continuity. Mass is conserved. This equation is Newton's law. There's MA and there's F. So F minus MA equals 0. That's F equals MA, but rewritten with, in the terms of magnetohydrodynamics. This is Faraday's law. But what we have implicitly in here is that this is the electric field. We assume infinite conductivity, and so our Ohm's law is E equals V cross B. And that's where that comes from. We have an energy equation. We assume the plasma is adiabatic. There's not much energy transfer except for conversion from magnetic field. And then, of course, no magnetic monopoles, divergence of B is 0. So we try to solve this set of coupled, nonlinear, partial differential equations in 3 dimensions on a computer. And we model it in a large grid, 5 times the distance to the moon, in a simulation grid that's shaped like a cylinder. And once we do the calculations, then we visualize the results. And here's just an image showing the kinds of things that we can do. We can make movies. We make individual images. We have very powerful image rendering software that we can create applications to view anything we want or to do calculations as well. For example, we can do calculations. This is actually the solar wind, or the plasma velocity. So red is positive towards the Earth and blue is away. So this is the solar wind flowing from the sun away that way. But we can, within this visualization program, do calculations like calculate the specific entropy along a magnetic field line. We can do very complex things to really try to get at the underlying physics. We make individual images, and we then string them together to make animations like this one that shows what happens to the Earth's magnetic field when we change the solar wind magnetic field. And what you see is that first it gets squeezed down, and then a piece breaks off, and I'll play it again. So Earth's magnetic field gets squeezed down, and then you see that little piece break off the tail. And those are the kinds of things that we study in trying to understand the physical processes that are involved. Actually, this is the same movie as before. So we use these things to do space weather prediction. The Halloween storms, this is a simulation of the Halloween storms, and what we did is we put in 2 communication satellites, actually the weather satellites, GOES 5 and 6, and from this we could calculate when did they go outside of Earth's magnetosphere. Out here is the solar wind, and the solar wind in this case was so intense it was squeezing down Earth's magnetic field, and sometimes those satellites popped out into the solar wind. And we want to be able to predict that, because some communication spacecraft use Earth's magnetic field to orient themselves. They don't use rockets to push and to keep themselves in position. They push off the magnetic field with an electric current. You know that if you have an electric current in a magnetic field, you get a force. So you can use that to push on the magnetic field and to keep your satellite aligned. But you have to make sure you're inside the magnetosphere to do that. So here's an example of calculations. The red line is the simulation, and the blue line is the actual data. So in some places, the agreement is not so good, like right here. But right in here, right there, right through here, we get pretty good agreement. So we can, in fact, use this simulation to predict when we're going to be inside or outside the magnetosphere. So to conclude, space weather does affect all of us, even though you don't realize it. Every time that you use telecommunications, you're probably connecting through a satellite. Farmers now are using GPS to help them plant, and so that cuts costs of agriculture, and if the GPS goes down, the costs go up. That gets passed on to us. Oil companies especially use GPS, and then there's issues of power transmission, all kinds of things that you don't normally think about, that the costs are passed on to the consumer. And as we become more and more dependent on space technology, space weather becomes more important to all of us. And there's lots of interesting basic physics to be done in studying space weather. And if you want to study space weather, or for that matter, particle physics, nanobio, things like that, UT Arlington is a good place to go. And Nadia has got information on our graduate programs and flyers on the physics department. You can always send me an email and ask me for information. And we are always looking for good students. And I know that the tech students are very good, and I'm very impressed with the university here, the students, the conference you put together, and you deserve to be congratulated. Thank you.
Interesante conferencia. Nuestra compañera Paulina Domínguez le hará entrega de un reconocimiento en nombre del comité organizador.
pulsate or something like that?
The color of the aurora depends on what levels of atomic excitation you have, because what's really happening is that energetic electrons are coming along the magnetic field, hitting neutral atoms, exciting them. And the most common colors you get are red and green. Red coming from an oxygen transition line at about 6,300 angstroms, and then a green line, which is a nitrogen transition line. Those are the most common elements in Earth's atmosphere, so those are the most common colors that you see. Now, as far as looking at the sun, anytime that you look at the spectrum of coming from an object, you can tell something about its elemental composition by looking at absorption and lines and things like that, so that you can see what are the electronic transitions in that. And that's how helium was discovered, because they saw certain spectral lines that didn't fit anything, and they decided maybe it's a new element, and so they took the Greek word helios to name the element helium. And first when they started seeing these very strange transition lines, they couldn't believe that it would be oxygen 7+, and maybe it was a new element, but it turned out to be oxygen 7+. So oxygen ionized so much that in such a hot environment that it loses everything except one electron.
And the magnitude of the magnetic field?
On the surface of the
Yeah.
sun? Oh, it varies. All right. In this room right now, we have about a third of a Gauss. In a sunspot, you might have 5,000 Gauss.
What's the most common color for explaining the sun increasing temperature from the solar chromosphere to the solar corona?
Microflares, reconnection, so twisting magnetic field. If I take 3 bundles of magnetic field and I twist them and I try to stack them together, between 2 of them they're going to have opposite magnetic field, which means there has to be a current flowing there, and that current can break down so that magnetic fields merge. Magnetic energy is then converted to plasma energy, mostly into heat, and that's going on all the time because you have all of this convection in the photosphere of the sun. And so that is occurring, but we're not sure exactly where or just how the magnetic field is broken down, and there's still a lot of the details that need to be confirmed. But the general opinion is that it's this ongoing convection converting plasma flow energy and convection energy, mechanical energy, into magnetic energy, and that's dissipated just above the photosphere, and that's because right above the photosphere, it cools off to the chromosphere to about 5,000 degrees. And then it starts to rise very, very rapidly. And probably it has to do with the amount of density. And because a higher density plasma can support more current. Once the density of the plasma falls, it can't support as much current. And the current is more likely to break down, leading to the release of the magnetic energy. But we aren't sure, because there's still disagreements on detailed models.
Is that related with the velocity? I mean, if the solar wind becomes supersonic after a region, and then it slows down or it accelerates?
Well, the solar wind, okay, so you have the hot corona, and then the transition to supersonic, that's still argued as well, because we've got some models of solar wind that can predict part of the solar wind, and others that other parts of the solar wind it can't, especially the very high speed, low density solar wind. Our models have trouble predicting that. So there's still questions about exactly how is that solar wind produced and from what part of the solar surface. Yeah, we have a rough idea of how we get the heat, and then once you get the heat, that will be converted to kinetic energy as the corona expands. But again, some of the details of that are not understood, because we know that some of that energy has got to be added after the transition point. It's like a supersonic afterburner. In an afterburner, you add fuel in the flow when it's supersonic. And when you do that, the combustion in the supersonic regime just adds to the kinetic energy of the flow. If you add the fuel in the subsonic regime, what you increase is the mass density of the flow, and actually you cut the kinetic energy per particle. So we know that part of the solar wind acceleration is occurring in the manner of a supersonic afterburner, that somehow energy is being added afterwards, and we think it's waves that are being propagated up from the solar surface that then are dissipated after the transition to supersonic. But again, there are a lot of arguments about how that happens, what are the instabilities that produce that energy transfer.
Whether it is produced by any reactions at the sun or anything else, is there a way to take advantage of all this amount of energy that is thrown to us from the sun, or a project in the AES or elsewhere?
I'm not sure exactly what.
Well, we've
What
got
is-
all
Hacer la
these.
pregunta en español si quiere.
Tenemos toda esta energía que viaja del Sol a la Tierra, en forma de protones y de todo el desprendimiento de masa que tiene el Sol, de la superficie del Sol. ¿No hay algún proyecto para encontrar una forma de aprovechar toda esa energía? Digo, es energía electromagnética y nuestra
Sí.
tecnología se basa en eso.
Se puede hacer, pero no es fácil. Because, well, for example, in Alaska, they talked about this, and they got money from the NSF to build a supercomputer, supposedly to do calculations to figure out how to harvest the energy. You could do it if you covered Alaska with copper wire. So it's not practical.
¿Alguna otra pregunta?
Well, this data is for our sun, which is yellow. How would the solar wind be for, say, blue stars, which are much hotter? And like, how would that compare to other solar systems? And what would the implications be for life in those solar systems?
Well, first of all, our sun went through various stages. Early in the history of the solar system, our sun was in a form called a T-Tauri star. And the solar wind was about 1,000 times more intense. And solar wind of that intensity actually stripped away the primordial atmosphere of all of the inner planets. The atmosphere that we're breathing now is not the original atmosphere of the Earth. The original atmosphere was removed, but then it was replaced by volcanic emissions and outgassing from the Earth. Mars lost its atmosphere over geologic timescales in part because it doesn't have a significant magnetic field, and so there was continual erosion of that atmosphere by the solar wind. So the interaction of a planet with its stellar wind is an important factor in whether life can survive on geologic timescales, because if you don't have an atmosphere, it's very, very difficult. Other stars, we know that other stars have got magnetic activity cycles. And as far as the characteristics of stellar winds for blue stars, I don't know. That's not my area, so I'm not sure about that. But we do know that many other stars have got magnetic activity cycles, and there's been data collected over the past 30 years for stars that are somewhat similar to our sun, the sun-like star catalog. And those show magnetic activity cycles very similar to our sunspot cycle, which is every 11 years. For sun-like stars, the range is anywhere from 7 to 14 years, so we're right sort of in the middle. The way that we make these kinds of measurements is by looking at a particular transition of calcium. That the line is split by the Zeeman effect, so that's a direct measure of the photospheric magnetic field. So you look at the Zeeman splitting of that line, that gives you a measurement of the local field. You do that over time, and you see the field goes up, the field goes down, magnetic activity cycle. So we know that other stars have got magnetic activity cycles like our sun, but I can't answer your question about, say, blue stars and what kind of stellar winds they have. But all stars are magnetized. Of that, we're pretty certain. And so all stars have some kind of stellar wind.
Una última pregunta.
There might be, observations of red giants, and people might have done those kinds of modeling and calculations, but I don't know what the outcome of those things are.
Thank you.
I'm not really an astronomer. I just play one on TV.
Muchas gracias, doctor Ramón López.
De nada. Gracias.
Los invitamos.